Circular logic, problem number 1, here. So we're going to do problem number 1 from circular logic. I'll do it kind of step by step so you can hopefully pause and rewind, review stuff as necessary. Okay, so what do we know? Well, our car's traveling around in a circle, and in doing that, it is experiencing an acceleration toward the center of the circle, otherwise it would veer off in a path tangent to the circle. In this case, all we're given is the coefficient of friction and a velocity, which doesn't seem like all heck of a lot. One quick aside, this is the static friction. As tires roll along the surface of the ground, they don't slide, hopefully. Drive safe. So it's the static friction, not because it's a mistake, even though it's in motion, it's the static friction because the tires aren't sliding against the surface of the road. So we're given that, and we're given the velocity, which is a really fast 25.6 meters per second. Don't drive in circles at that kind of a speed. So let's take a minute and see what we're given. So let's actually list how we're given. So we are given the coefficient of static friction is 0.73, and that the velocity of the car is 25.6 meters per second. Our car is traveling around in a circle. A bird's eye view of the road would look something like this, and it'll have our car. You'll see our car traveling around in a circle around that road. So bird's eye view, great. Okay, car travels toward this travels in a circle, which means that we know there is some sort of centripetal acceleration and some sort of centripetal force keeping it in that circle. So let's consider what it would look like if it were, well, if we were sitting behind it. So if you're sitting behind the car and the car is a square, artistically I'm going to be a little limited. So our car is a square, there's a gravitational force downward, there's a normal force upward. We're assuming that the road's horizontal. So because of that, these two forces are vertical. They don't impact the circular path of the car. The circular path is horizontal, these are both vertical. Essentially they cancel. They don't overall have an impact on the motion of the car. What does? Let's assume here that our car is going in that sort of way, so our car needs to make a right turn. The only force capable of exerting that is the frictional force. So there will be a frictional force that allows the car to make a right-hand turn. And if you've ever driven in a car or been in a car on ice, then you're aware that if your car can't grip the road, you're not going to turn very well. So friction exists, and it allows the car to make this turn. In this case, these two forces cancel. The only force responsible for the centripetal motion of the car is the frictional force. Therefore, this is the centripetal force. That's like the biggest and maybe most important idea of the problem. Frictional force provides the centripetal force. Centripetal force is provided by the frictional force. So we'll take that equation and we'll kind of run with it. But first, let's consider what we're asked. We're being asked the radius of the path. Okay, well, great. These aren't related really quickly or easily in an equation, so we can't just quickly solve it, which kind of stinks. But we do know that there's centripetal motion, there's a centripetal force, and this R pops up in conjunction with V when you're like doing some calculations with the centripetal force. So hopefully that'll help. Also, the static friction is the frictional force, but to find the frictional force we'll need the mass, which is weird, I think. Probably not. So we'll start with the idea that centripetal force is equal to the frictional force. Centripetal force is defined as mass times centripetal acceleration. Frictional force is defined as coefficient of friction times the normal force. In this particular case, since our car is on a horizontal surface, the normal force equals the gravitational force. Gravitational force, of course, equals mass times gravity. And we can assume that G is 9.8 because we're on Earth. Also, if we're substituting, we might as well keep going. Centripetal acceleration, by definition, is equal to the speed squared divided by the radius. Notice that's not velocity, it's the speed, the magnitude of the velocity. So let's go from there. So this will become mass times speed squared divided by radius equals the coefficient of friction times mass times gravity. Seem okay? So from here, it's the mass of the car in both situations. So the mass cancels with the mass. It's on both sides of the equation. So then we have v squared divided by the radius equals the coefficient of friction times gravity. And so we're looking for radius. I think this has come up many times before. But if your unknown is in the denominator of a fraction, it's always a good idea to move it to the other side of the equation. I think. So to move it to the other side of the equation, we'll multiply both sides by r, and this one will cancel with that one, so we'll get v squared equals the coefficient of friction times gravitational acceleration times the radius of the curve. We're looking for the radius of the curve, so to isolate entirely, we'll divide both sides by the coefficient of friction times gravity. By the way, just keeping algebraic stuff will certainly help when you get to number 5 also. So keep this kind of thing in mind in number 5. But in this case, we're done. The radius of the curve that must equal minimally the speed squared divided by the coefficient of friction times gravitational acceleration. So in this case, you do the math, you should find that the answer is 91.6 meters. So 25.6 squared divided by the quantity 0.73 times 9.8. And hey, lo and behold, the radius has to be a minimum 91.6 meters. That's a huge circle because it's a really fast speed. Drive slower than that. So that's number 1. Sounds good?